What time is it? It's time to learn. Hi there, Andy Malone, Microsoft MVP and Microsoft Certified Trainer. Welcome back to the channel. This time we're going to talk about asymmetric cryptography and understand exactly what it is and how it works, and also where you can use it. So if you like what you see, as always, go ahead, ring that bell, click on that subscribe button, and you won't miss any future postings. And as always, I love your feedback. So drop your questions below, and in the meantime, let's begin. And hope you enjoy. So Cryptography Made Simple Part 3. In this session, we're going to talk about the key security principles. We'll talk about principles such as defense in depth and end-to-end protection. We'll understand how asymmetric cryptography works, how encrypted email works, the Diffe-Helman algorithm, and we'll talk finally about some hashing functions. So when we talk about key security principles, if you pick up any computer book related to security, these are guaranteed going to be right at the beginning of that book. First of all, the principle of defense in depth. So you can imagine if you've been to the airport recently, to be honest, it's been a little while, hasn't it? But if you go to an airport, you can imagine that as soon as you walk into the airport, it has different layers of security. So before you can board your plane, you have to get through security. You've got to prove that you've got an airline ticket. You've got to show your passport, perhaps. Once you get through security, you do all the security checks and so on. So there's a number of different stages that you need to get to. And it's exactly the same, for example, in a data center or in a building where data is the heart of your operation. So you have to keep that absolutely secure. So on the perimeters, of course, we're going to have physical security, identity and access security. Things like, biometrics, maybe you'll be using Windows Hello for Business, something like that. The perimeter network, keeping that secure, firewalls, for example. Then you've got your network, compute, finally the applications, and at the core of everything, you've got your data. So ultimately what we're trying to do with encryption is we're trying to provide an end-to-end encryption solution. So you can see that different layers of the transport model, if you will, can operate different versions of encryption. So some of it's hardware-based, and of course some of it is software-based. So you pick up any computer book, you're going to see this on page 101. CIA. No, this is not the Central Intelligence Agency. This is confidentiality, availability, and integrity. And the idea is that, of course, confidentiality refers to the need to keep things confidential, such as sensitive data, customer information or PII, personally identifiable information, and so on. Integrity refers to keeping data or messages correct so that you can prove that they haven't been tampered with. And also, of course, availability, making sure available that the data is there when people need access to it. So confidentiality, integrity, and availability are three very important concepts. So encryption plays an equally important role in all of this. So encryption, of course, is the process of making data unreadable and unusable to unauthorized viewers. And this can come in a number of different flavors. Encryption of data at rest, such as using a symmetric key, and we discussed this in part 2 of this series. And you can go ahead and you can watch that if you've not seen this. Also, encryption of data in transit, which tends to use asymmetric encryption, and I'm going to explain that. And it uses a combination of both public and private key technology. So when we talk about understanding asymmetric cryptography, first of all, we need to know why we use it. Well, typically it's used for both encryption and decryption, also for things like digital signatures, as well as key exchange. Also, secure communications, such as TLS, Transport Layer Security, or SSL. These are all examples of technologies that use asymmetric cryptography. So when we think about the public cryptography, typically it uses a public-private key. The key space tends to be a lot smaller. And again, this is quite useful for both providing secrecy, but also providing authentication and integrity for services. So public keys are freely available. They scale much better since only a single key pair is needed per individual. It provides both authentication and also non-repudiation. And Diffie-Hellman, RSA, Elgamal, elliptic curve cryptography are all examples of this. So some examples of technologies that use asymmetric: web browsers, SSL for example, IPsec. IPsec is a security algorithm which negotiates. So once we've agreed that you are authentic, then we shake hands and we agree to negotiate a security algorithm. Virtual private networks, digital signatures, secure shell, multi-factor authentication, these are all examples of technologies that use asymmetric cryptography. Some really important examples include this: S-MIME, secure multi-purpose internet mail extensions. So it's a standard technology for sending email on a network. And as you can see, it's based on using certificates that work with a private key and a public key. So a certificate is issued from a trusting authority. The easiest way to think of a certificate is that it's like a passport. So it comes from a trusted source, the government, for example. So if you sign a message with the private key, it can only be validated by using the public key. And if somebody encrypts the message with the public key, it can only be decrypted with the private key. Hence the term public-private key technology. So S-MIME and digital signatures. Digital signatures, and I'm sure we've all had emails from our bank in the past. And our bank says, you've got a problem with your account. And often, a lot of it's spam email. And so how do we know that it's genuine, that it's come from a genuine source? Well, digital signatures are one technology that can help us do this. They provide security capabilities, including not only authentication, but non-repudiation and data integrity. So data integrity, you know that what was sent is what you've received. Non-repudiation means that you can't say, I'm sorry, I never received it, because it's audited. Also, authentication in a digital signature allows the recipient to know that the message was sent by the person or organization who it claims to have sent the message. The uniqueness of that signature prevents the owners of the signature from disowning it, hence the term non-repudiation. Integrity is a result of specific operations that make digital signatures possible. And as it says, although signatures provide integrity, they do not provide confidentiality. Applying digital signatures is a fairly simple process here. So at its simplest, as you can see, a signature works by performing a signing operation on the text in the email message, i.e. when the message is sent, and a verifying operation when the message is read. So you've got the sender and the receiver. So the body of the message is captured, a hash value is calculated, and we're going to talk about a hash value. It's a one-way encrypting algorithm, so it produces a fixed length output irrelevant of the size of the message. The sender's key is then retrieved. The hash value is then encrypted with the sender's key. Finally, it's encrypted the hash value is then appended to the message, and finally the message is sent. So verifying the signature, so when the recipient receives the message, the hash value is also retrieved as well as the body. The hash value is then calculated and the sender's public key is retrieved. The encrypted hash is decrypted with the sender's public key, and then it's compared with the calculated hash. Now, if the sender and the receiver's hash is the same, we know that it's genuine and that it's not been tampered with. So, as we've said, digital signatures provide integrity, but they do not provide confidentiality. So encryption, as we've said, is a way to change the content so that it cannot be read or understood until it is changed back into its readable form. Now, if you've not seen part 1 of this series, then go ahead and have a look at that. Message encryption provides 2 services, both confidentiality and data integrity. The message is encrypted by utilizing the recipient's public key, and the public key, as I've said, is available to everyone. Thus, the message encryption doesn't provide authentication, and therefore it doesn't provide non-repudiation. So this is one of the reasons why you need to use both. So message encryption makes the content of the message unreadable, but of course S-MIME, secure multi-purpose internet mail extensions, again provides both digital signatures and encryption. So ultimately, this is what you're looking for. You're looking for a total solution here, and that's what you can see that we've got. Okay, so decrypting the email, message is received. The encrypted message is received with the session key. The recipient's public key is retrieved. So the session key is decrypted with the recipient's private key. So I'm sending a message to you, your public key, and you are decrypting it with your private key. The message body is then decrypted with the session key, and finally the decrypted message is returned to the recipient. Fantastic. Now, digital signatures and encryption working together. Okay, so we've got both integrity and confidentiality here. So in this case, digital signatures and message encryption are not mutually exclusive. They are 2 services that can be used together. They can either be used together or they can be used separately. But you can see here, ultimately, this is how they come together. Now, these 2 gentlemen, Whitfield Diffie and Martin Helman, are considered to be the granddaddies of cryptography. Back in the day, they invented an amazing algorithm, and it was using a very simple premise. It used something called clock mathematics, and it went a little bit like this. So we've got Alice and Bob, and Alice generates a prime number. So she creates a secret private key. And from that private key, she derives a public key that she decides that she wants to share. And the idea is that it uses this very, very simple concept, and they called it a trapdoor function. So the idea is it's really easy to compute, it's easy to see the result, but not so easy to work out how it was created. Let me show you. So the concept is, we fly on planes all the time. I do. Well, not for a while, but, and so the plane flies. So let's say X, the plane flies. F is the trapdoor function. And when you get on a plane, of course, you know how a plane flies. But if you're faced with this scene, oh my goodness, you would think, oh, how on earth does that work? So Y is the cockpit. So in this case, let me give you another example. If I give you a number of X, 50,125,876, okay? So this is my public key, all right? And if I said to you, obviously you've got the trapdoor function, it's easy, to calculate a number like that on a modern calculator, but it's almost impossible to reverse engineer it. So how did I get to that number, 50,125,876? Okay, that's the trapdoor function. Okay, so y equals f over x. Okay, so they had this concept that it was so simple, it was brilliant, and it went a little bit like this. There was once an Arabian prince in the desert, and the Arabian prince had never wandered out of the desert, except one day he'd been invited to New York. So he went to New York, and he stayed in the finest hotel, and he saw a miracle. He switched on a tap, and water came out of this tap, and it was like nothing he'd ever seen in his life. So of course, he wanted it. So he decided to take a tap and take it back to the desert. And he stuck the tap in the ground. And of course, it didn't work. So in this case, given X as the tap with the running water, it's easy to see how it works. But given just the tap itself, it's almost impossible to reproduce Y, the infrastructure required to carry the water. So given X is your public key, it's almost impossible to derive how did I get that? What was the formula to get that? And that's the trapdoor function. It was simple, but absolutely brilliant. Okay, so this is the Diffie-Hellman key exchange as an example. So we have Bob and Alice, and in the middle we've got Charlie the hacker. And Charlie the hacker's trying to steal the secrets. So, of course, Alice says, I want to send a message to Bob. So she places the blue key, which represents the message here, into her chest, and she signs it with her red key and attaches a padlock. She then sends that securely to Bob. Now, Bob can see that it's come from Alice because Bob can see Alice's public key. So he knows that it's come from the right person. So he attaches his own padlock to it and again secures it. Now, again, Alice can see that it's come from the correct person. So she knows that Bob is the true recipient. So she removes her padlock, sends the message back, and Bob again now says, great, I can remove the padlock and open the box, and he can now read the message. Brilliant. Simple, but brilliant. Okay. Now, I also mentioned another type of function. This is called a hash function. And a hash function you can see here is basically a very fast one-way mathematical function that generates a fixed length result, and this regardless of the amount of data that you pass through it. So when we communicate with each other, you compare, or I would compare your hash with my hash, and if they are the same, we know that they are authentic and they've not been manipulated. Okay? Now, this is the easiest way to describe it. So if I had an input of a word fox, so the cryptographic function you can see is the output. So it's exactly the same size as output, irrelevant of what the text is. So even if you just change the O to an E or something like that, the output will change, and thus you will know that your file or your message has been intercepted. That's the principle of a cryptographic hash. So there you have it. Just a few quick security principles, the concept of defense in depth, and end-to-end encryption, understanding asymmetric cryptography, and also how email and Diffie-Hellman works. I hope you've enjoyed. Thanks for listening. So there you have it, a little bit of asymmetric cryptography. I really hope you found that useful and enjoyable. And remind you, this is part 3 of that 3-part series. So if you've not seen the other 2 parts, go ahead and watch them now and you'll learn something for free, because this is what this channel is about. Now remember, I'm planning new sessions, so I'm looking for some really good ideas from you guys out there. So are you interested in Exchange? Are you looking for stuff on SharePoint, for Teams, for Microsoft 365? I want to hear from you. Put out your suggestions down below there as well. Okay, so thanks very much for listening. As always, click on that subscribe button if you haven't subscribed. Come on, I need to get my numbers up, and also ring that bell so that you don't miss out on any future videos. Okay, thanks very much for listening. You stay safe, and I'll see you next time. Take care. Thanks for dropping by. Hope you enjoyed the video. Go ahead and click on the subscribe button and ring that bell, and you won't miss a thing. See you next time.